In today's lecture, we'll discuss the Cantor set. The Cantor set is a strange example of a subset of the real numbers, and it'll give you a sense of how strange and surprising certain subsets of the real numbers can be, and just give us an opportunity to discuss many of the concepts we've been talking about the last couple weeks in the context of a particular example. So the Cantor set to start with, Cantor starts with the unit interval from 0 to 1. And the first thing he does with this interval is removes the middle third of it. Okay, so I'll try to make this look as good as I can, right about there. All right, so this will be 1/3. So right here we have 1/3. And here we have 2/3. And we're removing this open interval from 1/3 to 2/3. All right, so we remove that. And so what we get is just these disjoint closed intervals, and I'll draw that for you. All right, so after we remove the middle third, we have these two disjoint closed intervals here. And Cantor's idea here is now we have two intervals instead of the one that we started with, and we're just going to do the same thing that we did to the first interval to each of these intervals. So we're going to remove the middle third of each of these intervals. So something like this, we have the middle third here. So that's going to leave us with, let's see, so 1/3 of 1/3 is 1/9. Right, so we have closed intervals of length 1/9 here. Right, so we have this closed part, we have this open part, which is 1/9, and then we have the last 1/9 there. So this is going to be at 2/9, and then 1/3, of course, is 3/9. And we're going to remove that part. And we do the same in the other subinterval. So 2/3, that is 6/9. So this will be 7/9 here. And then this will be 8/9. 1 being 9/9. And we're going to remove that. Okay, so that leaves us in the next stage with 4 closed intervals looking like this. All right, so we have 4 closed intervals now. And of course, we just continue this process. So we keep removing the middle third. So remove the middle third of that, remove the middle third of that, remove the middle third, and remove the middle third. Okay, so this process continues. And so the Cantor set is defined as what remains here. So the Cantor set equals what is left over. So the leftovers after repeating this infinitely. Okay, so that's the definition. You just keep taking the open middle third out of these closed intervals every time the number of closed intervals doubles, and so the number of them is getting larger and larger, powers of 2 numbers of them, but the length of the intervals keeps getting smaller and smaller. Okay, and so whatever is left over after repeating this infinitely is the Cantor set. And of course, this isn't a real definition, just sort of giving you the basic idea of it before we get into any rigorous particularities. So natural question is, well, is there anything left over after you repeat this infinitely often? So intuitively, yes, this is certainly going to leave something after after you do the infinite number of repetitions here. For example, 0 and 1, if we think about them, right? 0 and 1 are in here at the first stage, and then we remove the middle third here. That doesn't remove 0 and 1, so they stay here, and we remove the middle third of that interval. All right, that doesn't take out 0 and 1. We keep removing the middle third, but 0 and 1 are never in the middle third. They're always sort of over to the, 1 is all the way to the right, and 0 is all the way to the left. So 0 is always going to be sort of in the first third, never the middle third. 1 is always going to be in the last third, never the middle third. So that's not going to be, those aren't going to be removed. So we're definitely, sort of intuitively, according to this, going to have 0 and 1 in the Cantor set. And similarly, actually, every one of these endpoint of these closed intervals, every endpoint, you can convince yourself is going to be in the Cantor set as well. So, for example, taking 1/3, right? 1/3 is in there. We're removing this open interval here, so 1/3 and 2/3 are going to be remain after this first removal, but then, right, then just focusing on 1/3 again. 1/3 is in the final third of all of these subsequent intervals here. So it's the last third, not the middle third. So it's sort of never going to be removed. And so basically every time you get one of these endpoints, the endpoint becomes, is never going to be a middle third. So it's never going to be removed. Okay, so sort of intuitively speaking, all of these endpoints are going to be in the Cantor set. So this is sort of not empty. So intuitively, clear that every endpoint of the closed intervals in the construction remain in the Cantor set. Remain throughout each iteration, remain in each subsequent iteration. So not only is the Cantor set not empty, and let's say C is going to denote the Cantor set. So C. So not only is C not equal to the empty set, it should be at least countably infinite. So it seems to be countably infinite. Or sorry, I should say at least countably infinite. Because clearly the number of endpoints here, we start with 2 endpoints. In the next iteration after we remove, we have 4 endpoints, and then we have 8, and then we have 16. It's going up as a power of 2. So that's going to go to infinity as we go. So this seems to raise a natural question, and we can consider a list of questions we might ask about the Cantor set here. So here we have some questions. So first of all, are the endpoints the only thing in the Cantor set? So are the endpoints the only thing in the Cantor set? So if the endpoints are the only thing in the Cantor set, then it would automatically be countable. But maybe there's something else that's left, right? So just because we're surely not removing, well, it seems certain that we're not removing those endpoints, but is there anything else left in this after this infinite number of iterations? I don't think it's intuitively clear. I mean, it might seem might seem reasonable that maybe just the endpoints are left, but then again, I think there should be some doubt in your mind about whether that might be the case. So we naturally ask, are the endpoints the only thing left in the Cantor set? So if not, is it still countable? And so there might be other stuff, but maybe only a few other things, right? Or maybe just a countable set of other things. So it might still be countable. So is it still countable? Maybe it's uncountable. And then we might ask about the topological properties that we've been discussing. So is it open? Does it have an interior? Or the interior being the largest open set contained in a set. Is it closed? If not, what's the closure? Is it closed? What's the closure? What can we say about limit points? So what are the limit points of this set? What other things did we talk about? We talked about compactness and connectedness. So is it compact? Connected? All right, so things of this nature. So this is a whole list of questions we can test our muster on with this set. Okay, so I intend to basically address all of these questions in the next 2 lectures. Okay, so the first thing I'm going to do is we'll establish some intuitions about the Cantor set. So we'll sort of do as much as we can to get a sense of the Cantor set without being super rigorous. Just sort of referencing this discussion here to get a sense of some things, and then I'll be more rigorous coming up. Okay, so I want to give you sort of as direct access as possible to thinking about the Cantor set without being too rigorous first, and then we'll move on to the rigorous stuff. So the first thing is regarding the cardinality. So roughly speaking here, the cardinality question with the Cantor set can be addressed in the following manner. So every time you remove the middle third here, right? So we remove a middle third here, then we remove middle thirds here, and here, here, and here. Roughly speaking, what you're doing is, if you think about your real numbers, so write your real numbers in a ternary expansion, so in base 3, in other words. Okay, so in base 10, right, your decimals, everything is 0 through 9. So in base 3, everything's going to be 0, 1, 2, right? So everything in the interval from 0 to 1, you're going to have your decimal point, and then it'll have a 0 if it falls in this interval here. It'll have a 1 if it falls in this interval here. It'll have a 2 if it falls in this interval here. Then in the next decimal point, so if you started with a 0, you're in here, and then in your next decimal point, it'll be 0, 1, 2 according to which third of this interval you fall into, right? And if your first decimal point was a 1, you fell in here, and then you'd look in the thirds of that to say where you were for the second decimal point. And if you were a 2 in your first decimal point, then for the second decimal point, you would have 0, 1, or 2 according to whether you were in those thirds. And that sort of continues. Okay, so that's how ternary expansion works. And then, so basically, roughly speaking, everything in the Cantor set, you're always removing anything which has a 1. Right, so you're removing all of the real numbers which have 1s in their ternary expansion, roughly speaking, because actually in a technical sense, there's like a technicality that has to be addressed. It has to do with repeating decimals, sort of like in the in the real number case, when you have 0.9 repeating, that can be the same as 1. You have a similar problem with ternary expansion. So, 0.2 repeating at the end of a decimal is the same as a 0, right? Having an infinite string of zeros. But anyway, sort of ignoring that technicality for a second, basically, when you construct the Cantor set, you're removing everything that has a 1 in the ternary expansion. So anything that has a 1 in the first decimal place gets removed. And then anything after that, when moving into the second decimal place, if it has a 1, it gets removed. Right? If it has a 1, it gets removed. And so you're removing everything with a 1. So roughly speaking, what you're left with, so for cardinality, so what we want to do is, so think ternary expansion of real numbers. So in the remove middle third construction, so remove the middle third, construction, we're ditching every real number, ditching every real number that has a 1 in any decimal place, of the ternary expansion, has a 1 in any decimal place of the ternary expansion. Again, as I said, I'm sort of glossing over technicality. I don't want to get bogged down in that. Because this argument, as I said, this is sort of an intuitive argument, plausible argument, and we're going to give a rigorous argument later that about the cardinality of the Cantor set. So I don't want to deal with the technicalities here. So we're removing every real number that has a 1 in any decimal place of the ternary expansion, and so what that translates to is the Cantor set. So C is all the real numbers that can be represented with only 0 and 2, with only zeros and 2's in the ternary expansion. Okay, so for example, you have you could have something like 0, 2, 0, 2, 0, 2, 0, 2, etc., or something that looks more random, 0, 0, 2, 2, 2, 2, 0, 0, 0, 2, 0, 0, 2, 2, all right, something like that. These would be elements of the Cantor set. Right, these are ternary expansions, okay, not decimal expansions. Well, with this in mind, it's pretty immediate that the Cantor set must have uncountable cardinality, because we can just do a diagonalization argument, right? Any possible list of elements of the Cantor set, we have, right, a list of a bunch of things with zeros and 2's. We can create something that's not on this list by going down the diagonal and just changing the digit, right? So if you see a 0 in the first sort of decimal, I shouldn't say decimal, it's tricimal or something. But I'll just say decimal. So if you see a 0 here, right, the first element on your list, you would write down a 2. And if you see a 0 here in the second element, the second decimal place of the second element, you write down a 2. And then your third one, you look in the third decimal place. If it's a 0, you write down a 2. If it's a 2, you write down a 0. And so then you can construct an element of the Cantor set that disagrees in the ith decimal place with the ith element on your list. And so you can write down something that's not on your list. It's just a standard diagonalization argument. So diagonalization argument shows that C is uncountable. Okay, so that, at least intuitively, glossing over some details, shows you that the Cantor set has to have more than just those endpoints. In fact, has to have much more because it's, in fact, uncountable. So another way to go about arguing this is to assign to each element of the Cantor set a binary address. So instead of focusing on the removal of the middle third, you can say for any element of the Cantor set, it has to be either in this interval here or this interval here, right? So we can assign a 0 if it's here and a 1 if it's here. And then, but furthermore, it has to be in, if it's in this thing here, it has to be in either this or this. Right, so if after we've assigned a 0, in the next digit we can assign either a 0 or 1 according to whether it's in here or here. And similarly over here. So if we assigned a 1 in the first digit, we can assign a 0 or 1 according to whether it's here or here. And then once you've assigned 2 digits, then you can further assign a third digit. If it's, if it was a 0, 0, then it gets a 0, 1 according to whether it's here. If it's a 0, 1, it gets a 0, 1 accordingly. If it's a 1, 0, then it gets a 0, 1 accordingly. And if it's a 1, 1, then it gets a 0, 1 accordingly in the third digit. And it goes on like this. So you can assign to every element in the Cantor set sort of a unique infinite binary address. And the set of sequences of zeros and ones, those binary sequences, are uncountable by the exact same argument here, right? So any list of binary addresses, you can always construct something that's not on the list by just switching the digits down the diagonal. Okay, so alternatively, one can assign a binary address to elements of C according to which of the two closed intervals I guess I could say closed subintervals it is in sequential stages of the construction. All right. So anyway, that's two different kind of arguments. Oh yeah, and then I should say, and then diagonalization argument again. Then use diagonalization. So in either case, there is a kind of natural diagonalization argument. And there's two different ways you can think about that diagonalization argument to show that the Cantor set should be uncountable, to argue that it should be uncountable. All right, so the Cantor set we've convincingly, I think, argued is uncountable. But the question is sort of how big. So in some sense the Cantor set is big, right? So you have this. So it's uncountable. It has the same cardinality as of the real numbers. But there's another way of looking at the Cantor set, which suggests that in fact it's actually quite small. And so this is kind of puzzling. You have it's large in a set theoretic sense, but in a sort of more geometric sense, it's actually rather small. So to see that, let's go back to the construction of the Cantor set. And we'll write out some things a little bit more explicitly. So in our first stage of our construction, we start with the interval 0, 1. Right? And then in the second stage, we have the intervals 0 to 1/3 and 2/3 to 1. So now we have two intervals of length 1/3. Right? So we've the sort of total length of what's remaining is 2/3 of what we started with, right? We started with an interval of length 1. Now we have 2 intervals of total length 2/3. And then in the next stage, we have 4 intervals of length 1/9. So that's 4/9, and that's 2/3 of what we had previously. Right? And it's not hard to see every time you do this construction, right? Things shrink by 1/3, right? So each of these intervals in the next step of the construction after 1/9, it's going to go down to 27ths, right? Each of these this little closed interval in here, right? Those will be 1/3 of the intervals that we had in the previous stage. So we'll have 27ths, and there's going to be 8 of them, right? Everything doubles. Each interval, you have a first third and a final third. So for each interval here, we get 2 intervals in the subsequent stage of the construction. So we'll have 8 intervals of length 1/27, so 8 27ths, so that's 2/3 times 2/3 times 2/3. Right, so we have a power of 2/3 for every sort of stage of the construction. And so we see that as the number of stages of our construction go to infinity, the sort of size of our Cantor set is going to be 2/3 to the n as n goes to infinity, which is, of course, 0. So in some sense, the length of our Cantor set, not being very particularly careful about length, using it in a rather cavalier way, we would say the length of the Cantor set is equal to 0. So what we can note, if we set, so letting C0 be equal to our starting interval of 0, 1, C1 to be the interval 0 to 1/3, union 2/3 to 1, and then C2 to be the interval 0 to 1/9, then we have 2/9 to 1/3, and then union 2/3, so that's 6/9 to 7/9, and then we have 8/9 to 1, and then etc. So our Cantor set, C, is just the intersection of all of these intervals. Right? These are all nested. We're just taking whatever's left. After we keep removing things, that's going to be the intersection of all of them. So this is from n goes from 0 to infinity. And what we can do is note that sort of the length of, so if I'll just say, I'll use this absolute value symbol to denote the total length of this Cn. So the sum of the lengths of all of the intervals. This is equal to, we have 2 to the n intervals of length 1/3 to the n. So that's 2/3 to the n, right? And so the length of these Cn are going to 0, right? Since 2/3 is less than 1, as n goes to infinity. So this suggests that sort of the size of the Cantor set, and I should say explicitly whatever this means, we're just being a bit cavalier, sort of exercising our intuition here, is 0, or should be 0. So while the Cantor set is uncountable, it's rather large in a set theoretic sense, it seems to be in this sort of more geometric sense of a kind of size or length to be rather small. Sort of has the same size as just a single point. So what we find is, so we conclude is that C is large set theoretically. C is large from a set theory perspective. But small from a more geometric perspective, from the geometric perspective of length or size. So there's not really any contradiction here other than just the sense of, I don't know, it kind of violates our intuition in a way. We have this very large set from a set theory perspective, but that is completely divorced from our sense of size in a geometric way of thinking about things. So one corollary of this, and I guess I'm using corollary a bit loosely here, given that we're not being super rigorous. But a kind of corollary here is that the Cantor set is definitely not open, and in fact, it's sort of as far opposite from open as could possibly be. So the Cantor set isn't going to contain any open interval, right? If the Cantor set had any kind of interior whatsoever, right, contained any open set, then it would have to contain some open interval. But an open interval has length, right? And the Cantor set, we've argued, has zero length. So C cannot contain any interval. Any interval, no matter how small. And so what we would conclude is that the interior of the Cantor set is equal to 0, or is equal to the empty set. So thus, the interior of the Cantor set is the empty set. And in particular, it's not open. In particular, C is definitely not open. Okay, so hopefully that gives you some sense of the Cantor set, sort of counterintuitive as it is in a way. It's this kind of weird smattering of points in 0, 1. There's uncountably many of them, but on the other hand, it's rather sparse in the set 0, 1, in the sense that it doesn't have any kind of heft to it. It takes up. So in a way, it's uncountable, but it takes up a negligible portion of the interval from 0 to 1. All right, so that's basically going to conclude the intuitive introduction to the Cantor set. I want to move to discussing it in a more rigorous fashion so that we can discuss all of these questions and answer them and leave no doubt about their veracity. About the only one I'm not going to discuss is the fact that the Cantor set is not connected. That should be obvious. So the Cantor set has to be contained in the union of these two disjoint intervals here, 0 to 1/3 and 2/3 to 1. So you should be able to easily show that the Cantor set is not connected just from that piece of information there. But I do want to address all the other points and prove the things we've talked about in a more rigorous manner. So we're going to move now into a rigorous definition of the Cantor set and proofs of the properties that it has. All right, so to define the Cantor set rigorously, we're going to define a sequence of closed sets that are contained in each other. So they're going to be a nested sequence of closed sets. And the closed sets are just going to be the union of those disjoint intervals that we discussed above in the construction of the Cantor set. So we'll define, so C0 is just going to be the interval from 0 to 1. And then let's look at the picture up here of the Cantor set. So to get from 0, 1 to the interval from 0 to 1/3 and the interval from 2/3 to 1/3, I'm not going to define the next step by removal. I'm going to define it in a different way. So another way of seeing how to get from the first step with 0, 1 to the next step is we take 0, 1, we shrink it by a factor of 1/3. That gets us the interval from 0 to 1/3. And then we translate that interval by 2/3. That gives us the interval from 2/3 to 1/3. So that's the second stage of the construction. And then the cool thing is, once we've done that, so if we take those two disjoint intervals, shrink that by 1/3, that gives us these two intervals here, and then their translation by 2/3 gives us the other two of the four intervals in this next stage. And we just keep iterating that. So if we take those 1, 2, 3, 4, shrink this whole picture by 1/3, that gives us 1, 2, 3, 4 here. And then if we translate that over by 2/3, that gives us the other 4 of the 8 intervals in the next stage of the construction. So that's what I'm going to do here to define the Cantor set. So we have C0 is equal to the interval from 0 to 1, and then we're going to define Cn plus 1 in terms of Cn by, we'll take the set Cn, we'll multiply everything in it by 1/3. Okay, so this denotes the set of everything you can get from the set Cn by multiplying by 1/3, and we're going to union that with that same set, but then translated by 2/3. So this is going to be union the set 2/3 plus 1/3 Cn. Okay, so this set here denotes, it's all the y such that y equals 2/3 plus 1/3 x, where x is something in Cn. Okay, so I think the notation is pretty intuitive. And so what we want to do, so we're going to define, so let's see, we define the Cantor set to be the set C, which is the intersection, n equals 0 to infinity, of all of these Cn's. Okay, so what we need to argue, or what we're going to argue, is that all of these sets are nested inside of each other. And so what we're going to have is a nested sequence of closed and bounded sets. So since they're nested, they're all going to be contained in 0, 1, so they're going to be bounded, and they're going to be closed since they're just sort of inductively a union of closed intervals, finite union of closed intervals. And so we'll have this nested sequence of compact sets which are non-empty, and so we have a general theorem that says when we do a intersection of nested compact sets that are non-empty, then the result is a compact set which is non-empty. So that's going to tell us that our Cantor set is a compact set which is not empty. Okay, so that's sort of the plan. So our first proposition is that each Cn is a disjoint union of 2 to the n closed intervals of length 1 over 3 to the n. And furthermore, Cn plus 1, they're nested. So Cn plus 1 is contained in Cn. So the proof, so the first statement is a straightforward induction. Okay, so it's clear that it's true for C0, and then if you have, in the inductive step, if you have that Cn is a disjoint union of 2 to the n closed intervals of length 1 over 3 to the n, you just write down that union, and you apply this operation to it, and what you're going to find is that right, so this 1/3 c to the n, that gives you that gives you 2 to the n closed intervals of length 1 over 3 to the n. And then when you translate by 2/3, that's going to give you another 2 to the n closed intervals of length 1 over 3 to the n. And so you have 2 to the n plus 1 closed intervals of length, of length 1 over 3 to the n plus 1. I should have been saying n plus 1 because of the 1 over 3. All right, so this is sort of a straightforward induction. So the first statement is a straightforward induction. Induction argument. So I'll just omit that. I think it's pretty straightforwardly clear. So we also proved so the second statement will also follow by induction. So the second, so the statement Cn plus 1 contained in Cn will also follow by induction. So since C0 equals the interval 0, 1 by definition, and C1 is the interval 0, 1/3 union 2/3, 1/3, just by a straightforward computation, it's clear that C1 is contained in C0, so we have the n equals 0 base case. So now suppose that Cn plus 1 is contained in Cn for some n. So then Cn plus 2, by definition, that's just 1/3 Cn plus 1 union 2/3, so you're translating 2/3 plus 1/3 Cn plus 1. And by our induction hypothesis, the Cn plus 1 is contained in Cn. So the 1/3 Cn plus 1 is going to be contained in 1/3 Cn, and the 2/3 plus 1/3 Cn plus 1 is contained in the sort of an analogous thing with Cn. And that, by definition, is Cn plus 1. Okay, so that completes the induction step, and therefore the proof. Okay, and so a corollary is that C is compact and non-empty. Okay, and so why is that? Well, so note that each Cn is compact. So is compact since it's a finite union of non-empty closed intervals. I guess I'll just say compact and non-empty. Since it's a finite union of non-empty closed intervals. I'll just say compact intervals, compact sets. Okay, so the compact sets in question here are just closed intervals, right? Any closed interval is closed and bounded, so by definition it's compact. So therefore C is a countable intersection of nested, nonempty, compact sets. And we proved that such a set is nonempty and compact. And so remember, the nested interval property actually extends to compact sets. So we have a sort of nested compact set property. And so we know that such an intersection is nonempty, and the arbitrary intersection of compact sets is compact. Okay, so that completes the proof there. So that tells us that not only is the Cantor set closed, but it's actually compact as well. All right, so it's not going to be enough to know that the Cantor set is non-empty. We're actually going to show that the set of endpoints, as we discussed before, is contained in the Cantor set. So it's very helpful to know that we have this countable subset of the Cantor set. So that set's actually going to help us prove some other things. So we have the endpoints. So the endpoints all right, so what we can do is, so we define E0, so E for endpoints. This is the set with just 2 points, 0 and 1. So this is the set of endpoints of C0. So define E0 to be that, and then En plus 1 to be equal to 1/3 En union 2/3 plus 1/3 En. Okay, so this is clearly just, right, we're taking the endpoints of the C0 interval, and then we're just, right, then in the next step, that's just going to be the endpoints of, right, so after E0, we're just going to get the endpoints of E1, right, because this is just the same definition as for the C n plus 1 set in terms of Cn. So the endpoints are just going to get sort of carried along there. So this is clearly, so then clearly En is the set of endpoints of the disjoint closed intervals which constitute Cn. And so let's define, now define E to be the union of all of these ENs. Okay, so this is going to be the endpoint set, and we're going to show that this is contained in the Cantor set. So proposition. So we don't really strictly need this fact, but it's sort of related to the fact of the Cantor set that the Cn sets are nested in each other. In fact, En is contained in En plus 1. Okay, so in the next stage, we're adding more endpoints onto the to the previous stage, and 2. E is contained in the Cantor set. So let's look at the proof here. So proof of 1, E0 is just the set 0, 1, and E1 is the set 0, 1/3, and then take that set and translate it by 2/3. So we have 2/3, 1. So E0, that's clearly contained in E1, gives us a base case. So if we just suppose that En is contained in En plus 1 for some n, then En plus 1, well, En plus 1 is just equal to 1/3 En union 2/3 plus 1/3 En, and En is contained in En plus 1, so this is just contained in 1/3 En plus 1 union 2/3 plus 1/3 En plus 1, and that is equal to En plus 2 by definition. So this proves 1 by induction. So 1 is proved by induction. Okay, so number 2. So what we'll do is, we'll show that En is contained in C for each n. So we'll show that. So if we show that is, so En is contained in C, then the union of all the Ens is contained in C. And so for each, so we need to do this for each n, so we'll show this by induction. For each n by induction. Okay, so we need to do E0 first. So we first need to show that each of 0 and 1 are contained in the Cantor set. So we first show that E0 is contained in C. And remember, C itself is an intersection. So this is the intersection of Cj, j equals 0 to infinity. I'm using j not to conflict with the n. So what we have to show is that 0, 1, this set, is contained in all of the Cj. And so, in fact, we'll do that by induction. So we need to first show this by showing that E0 is contained in Cj for all j by induction. Okay, so our base case of this induction itself involves an induction. We have an induction inside an induction. It's the classic induction turducken. So since clearly E0 is contained in C0, since C0, remember, is just 0, 1, the full interval, closed interval. So suppose E0 is contained in Cj for some j, then, so what we'll do is write 0. So 0 is 1/3 times 0. So this is an element of, 1/3 times Cj, right? Since Cj contains 0, right? By our assumption here, and 1/3 Cj, that is contained in, by definition, Cj plus 1. Okay, so indeed 0 is in Cj plus 1, and 1 is equal to 2/3 plus 1/3 times 1. And that is an element of 2/3 plus 1/3 times Cj, right? Since 1 is in Cj by our assumption, and this is contained in Cj plus 1 by definition of Cj plus 1. So E0 is contained in Cj plus 1. Okay, so thus Thus, E0 is contained in C. So thus, E0 contained in C follows by induction. And this is the base case of our first induction. This establishes the base case of our first induction. So now suppose that the En, so En is contained in C for some n. Well, then En is contained in Cj for all j. So En plus 1, that being 1/3 En union 2/3 plus 1/3 En, that is contained in 1/3 Cj union 2/3 plus 1/3 Cj. And that, by definition, is Cj plus 1. So thus, En plus 1 is contained in Cj plus 1. So this statement held for all j. That's j going from 0 to infinity. So this is for j from 0 to infinity. For j greater than or equal to 0. Okay, so it's in all of the Cj's except for maybe C0. But remember, these C's are nested, so all of these C's are in C0. That is En plus 1 is contained in Ck for k greater than or equal to 1. But Ck is contained in C0 for any k. So En plus 1 is also contained in C0. And so this implies, thus En plus 1 is in all the Ck, and it follows that En plus 1 is in the Cantor set. Okay, so that's the inductive step. So this completes the inductive step. Step is complete, and so the proof is complete. Okay, so this gives us a concrete, countably infinite set inside the Cantor set. Okay, so the Cantor set is at least countable. We've rigorously established that at this point. So having this countable subset, this explicit countable subset of the Cantor set, is useful in a way that's kind of analogous to the rationals inside the reals. So the rationals is a very useful countable subset of the reals, and the utility of this endpoint set in C is somewhat similar, and the analogy basically holds because in the real numbers, every real number is a limit of rational numbers, and similarly, every element of the Cantor set is a limit point of this endpoint set. So we have the following proposition: is that every element of C is a limit point of E. And so as a consequence, the closure of this endpoint set is the Cantor set. Okay, so let's take a look at the proof. So the basic idea is that if you have X in the Cantor set, then this element of the Cantor set, right, I mean, sort of what you see above it is this stack of intervals, right? So you have this, you have intervals, and then you're, sort of cutting out the middle third. So it's going to be, it would be in, say, the first third here, and then maybe it's in the second third of that, and then it's in the first third of the next one, right? You see this stack of intervals above it like this, and so if you put any little epsilon neighborhood around X, eventually these closed intervals, right, we know their length is 1 over 3 to the n, if this is in the Cn stage here. So once that, the size of that 1 over 3 to the n is less than epsilon, then we're going to know that both of the endpoints of that interval is inside this epsilon neighborhood of X, and so that's going to tell us that X is a limit point of this endpoint set, right? These are endpoints that are in this E set, so that's going to imply the conclusion. So that's the basic idea of the proof. So let X be in C, and epsilon greater than 0 be given. So what we can do is take n, so choose any n such that, and this is, I guess it's in the natural numbers, such that 1 over 3 to the n is less than epsilon. So since X is in the Cantor set, it's in C sub capital N, right? The Cantor set is contained in, right, the Cantor set is the intersection of all those Cn's, so the Cantor set is contained in a particular one. So we have then X is in C sub big N, which is, as we know, it's a union. So we have A, I, Bi of closed intervals, and there's 2 to the n of them, 2 to the big N. So X is in that union where Bi minus Ai is equal to 1 over 3 to the big N. Right, so that's the length of that interval. So X is in one of these intervals, right? So X, so we have not Bi, sorry, Ai less than or equal to X less than or equal to Bi for some I. Well, then the distance between X and Bi is Bi minus X, and minus X is less than or equal to minus Ai. So this is less than or equal to Bi minus Ai, and that, as we know, is equal to 1 over 3 to the big N, and that's less than epsilon. And we also have the distance between X and Ai, that's equal to X minus Ai, and X is less than or equal to Bi. Right, and so what this says, so thus Ai and Bi are in the epsilon ball around X, right? In other words, just the interval X minus epsilon, X plus epsilon, open interval. So in order to say, so what we want to say is that we have elements of this endpoint set in the punctured ball around X, right? So remember, for X to be a limit point of the endpoint set E, what we want to say is that there are points in the epsilon ball around x that are not x itself, right? So it could be that x is one of these AI, bi, but it can't be both, right? So since x cannot be both AI and bi, it must be that there is an element, there is an element of E in the punctured epsilon ball around x. Or so AI and BI, these are endpoints of these CNs, right? So these AI and BI are the elements of E. Okay, so it could be that AI is X, but then BI is something that's not X in this punctured ball, and it's also in E. And it could be that X is BI, but then, right, then you'd have AI not being equal to X in this and in E. So thus, X is a limit point of E as claimed. And so what we have now is it follows that, so the Cantor set, we know that's contained in the set of limit points of E, right? So this is contained in the closure of E. So the closure of E is E union with its limit points. And so we know that the Cantor set is contained in those limit points. But E itself is in the Cantor set, right? So E is in the Cantor set, so this is contained in C closure, but C is a compact set. This is a closed set, so this is equal to C, right? So in fact, these inclusions have to be equalities, right? So we have C contained in E closure and E closure contained in C. So therefore, C is equal to E closure. The last thing I'll show in this lecture is that the Cantor set has empty interior. So this is just going to follow from the fact that there can't be any intervals contained in the Cantor set, as we discussed intuitively before. So for each n, let U sub n be Cn complement. And this is the complement in the interval 0, 1. This is 0, 1 minus the set Cn. Okay, so this set is a union of disjoint open intervals, right? Just because Cn is a disjoint union of closed intervals. It's a union of disjoint open intervals. And I want to talk about the length of these sets. And so we'll just sort of define a rough notion of length for unions of disjoint intervals. So if we have if S is a set which is a disjoint union of intervals of, let's say, closed respectively open. And so they can either all be disjoint closed intervals or disjoint open intervals. Open intervals let absolute value of S denote the sum of the lengths of the intervals, which constitute S. Okay, well, so in this case, so we have, as we know, the length of Cn This is, we have 2 to the n intervals of length 1 over 3 to the n. So this is 2 over 3 to the n. And un being the complement of Cn in this interval of length 1, it's not hard to establish this rigorously. This is just 1 minus 2/3 to the n. So what I want to note here is, so note that since the Cantor set is contained in any one of these Cn's, then by just taking complements, we have, so the complement of Cn, that's un, that's contained in the complement of the Cantor set. And this complement, again, is with respect to the interval, closed interval from 0 to 1. So thus, the complement of the Cantor set contains a union of disjoint open intervals with length as close to 1 as we desire. So with length arbitrarily close to 1. Right, so the total length of those disjoint open intervals is this quantity here, and as n goes to infinity, this goes to 0, so this goes to 1. And so we can use this to prove, this proposition. Which is that the Cantor set can't contain any intervals. So if x is in the Cantor set, then the interval x minus epsilon, x plus epsilon, is not contained in the Cantor set for any epsilon greater than 0. So consequently, the interior of the Cantor set is empty, and every point of the Cantor set is a limit point of the complement of the Cantor set. And there's, I guess, one other thing, so I'll just add in a comma here, and so the boundary of the Cantor set is just the Cantor set itself. And the basic idea of the proof here is quite simple from what we've done. So if you have x in the Cantor set and you have this interval from x minus epsilon to x plus epsilon, this thing has length 2 epsilon, right? And then the complement of the Cantor set we know contains all of these un sets. So we simply take un to be, and so we have this un as this sort of disjoint union of finitely many open intervals, right? But we can make all of this stuff as close to 1 as we would like, and so we make it close enough to 1 so that when we add 2 epsilon to that quantity, that exceeds 1. But of course, all of this is supposed to be contained in the interval, in the closed interval from 0 to 1. Right, so that's going to be a contradiction. Right, you can't have a disjoint union of closed intervals contained in 0, 1 whose length is larger than 1. Okay, so we're simply going to take our n large enough that 1 minus 2/3 to the n is within 2 epsilon of 1. Okay, so that's the basic idea. All right, so let me get rid of this. All right, let x be in C, and suppose that x minus epsilon, x plus epsilon is contained in C for some epsilon greater than 0. Then take capital N in the natural numbers such that, just as I said, we want 1 minus 2/3 to the n to be within 2 epsilon of 1. Okay, so in other words, we just want 2/3 to the n to be less than 2 epsilon. Okay, well, so then we have u sub big N, that's contained in the complement of the Cantor set. And x minus epsilon, x plus epsilon is contained in the Cantor set, right? So we have x minus epsilon, x plus epsilon union the un set is a disjoint union of open intervals in the interval 0, 1. But however, the length of this set, of this disjoint union, is 2 epsilon plus the un is 1 minus 2 over 3 to the n, right? But 2 epsilon, but this is 1 plus 2 epsilon minus 2/3 to the n, right? And from this inequality here, that's strictly greater than 0. So this is bigger than 1. Which is a contradiction, which contradicts the fact that the length of the interval from 0 to 1 is equal to 1. So thus, x minus epsilon, x plus epsilon cannot be contained in the Cantor set. Okay, so consequently, the Cantor set can't contain any non-empty open set since such an open set would contain an interval by definition. Would by definition contain an interval. So since the interior of the Cantor set is an open set, in the Cantor set, it therefore must be empty. It must be empty. So the fact that, additionally, the fact that x minus epsilon, x plus epsilon is not contained in C for every epsilon, epsilon greater than 0, and x in the Cantor set means that x minus epsilon, x plus epsilon intersect the complement of the Cantor set must be non-empty. So that tells us that x in the Cantor set is a limit point. Of the complement of the Cantor set. Okay, so remember, so x is a limit point if whenever you put an epsilon ball around it, it intersects the set in some point other than itself, right? But if X is in C, clearly then X can't be in C complement. So this being non-empty means there's elements of the complement in the punctured open ball there. And then finally, the boundary of the Cantor set, that's by definition the closure minus the interior. So the complement of the interior in the closure, but the interior is empty. So this is just the closure of the Cantor set, and the Cantor set is closed. So that's just C. So this is since the interior is empty and C is closed. Okay. So that proves some qualities of the Cantor set. So the Cantor set, right? So it follows from this also, right? I mean, so the Cantor set is not open. So for a set to be open, it has to equal its interior. So maybe I should have added that. So as a consequence of this, so C is not open. Okay, so we've seen a number of properties of the Cantor set related to the notions of open and closed and limit points and compactness. And next time we'll tackle the question of the cardinality of the Cantor set and talk about some other properties of it. Okay, so just a little bit more on the Cantor set in the next lecture.